Okay, guys, good morning. Welcome back to College Algebra. I don't know if you noticed the name of the meeting, but don't worry about the name of the meeting. I'm reusing an old link because I don't want it to sit in my meetings forever. Today, we're going to do everything we can to get you ready for exam 2. Exam 2 is going to be on Thursday, remember. So I figured I have some activity problems that we can try to work together. The group activities thing doesn't work quite as well in Zoom. So technically today is an activity day and I am going to give you something to work on. But I first want to just take any homework questions that you guys have. So I figured we'll treat the first, 30, 40 minutes of today as review. We can work whatever problems you guys want to work. And then we can spend the last bit of the class doing some of these problems from activities that I would normally do in class. So, maybe one other thing. Let me show you before we get started. Yeah, the other thing here. This week, I'm not opening up any fresh homework. I'm just opening one more assignment, and it's a review for exam 2. So if you look here, right, quiz 4 and all of that was open last week. The only new thing today, and the only new thing this week is this. And it's opening today, and it's due on Thursday at the start of class. So this review for test 2, this is the only thing you have to work on between now and the test. The test is next class, Thursday. And I would like you to get in here and start working on this immediately. If you haven't finished any of this older stuff, like homeworks 12, 13, or quiz 4, just send me an email or a Canvas message. I would be happy to extend any of those for you if you do need to work on them. And I really do encourage you to make sure you've finished all of these homeworks before the test. All right. So that's all from me. I'm not dropping any new mathematics on you guys today. I just want to practice whatever it is that you guys want to practice. So from any of these past homeworks, or if you want to open up and look through that exam review, if there's anything in there that you're really worried about, you'd like to take a look at, I am all yours today. What do you guys want to do? So like we did with our previous exam review, just type like homework 10, problem 7, or whatever in the chat if that's what you want to see. I think I can only have one of these. I would like to open all of these kind of preemptively, but I think I can only open one of these at a time. Homework 1229. All right. Okay. I see. So this is a problem in several parts. Bird population equals this. This doesn't look like the whole problem here. Homework 12.9. Where's the rest? Oh, maybe this is the key. Yeah, okay. All right, so bird population can be modeled by this polynomial. X equals 1 corresponds to June 1st. X equals 2 corresponds to June 2nd, etc. Find the days when F estimates there to be 3,500 birds. Okay. So this is homework 12, number 29. The bird population, I'll say X days into June. So like X equals 1 is June 1. X equals 2 is M2 is modeled by, and where's my polynomial here? X cubed, f of x equals x cubed minus, I don't know, where are we? X cubed minus 63x squared plus 942x plus 2,620. And they want us to find find the days when there are or were 3,500 birds. So for a minute, ignoring the actual mechanics of how to solve the problem, ignoring the actual algebra steps we're going to need, can somebody give me a kind of high-level overview of what it is that we're trying to do? What sort of equation or inequality or whatever is it that we need to solve here? Remember, you can hold down the space bar like a walkie-talkie to talk. Feel free to just shout out. What is it I need to do with this in order to answer this question?
Did you say just go ahead and answer it?
I couldn't quite hear the suggestion there, Mark.
You could graph it on your TI and then see on the tables where it hits 3,500.
Yeah.
But because the numbers are really large, it's very hard to see it. But that's one way to do it.
That's good. Yeah. So what Mark is saying is you can enter this into your table. So we open up our calculator, turn on our calculator, open up the y equals to input this function. So I say, okay, my function is x cubed minus 63 x squared plus 942x plus 2620. And certainly if I hit graph here, yeah, I wouldn't expect to be able to see anything on the default viewing window because these numbers are large. This function is not super simple in its behavior. Now, I know that there are 31 days in June, right? 30 days, that's September, April, June, and November. So the only x values I'm interested in are 0 to 30. I don't care about negative ones, but I do need to go at least up to 30. And it looks like we're talking about large numbers of birds, right? 2,620, 3,500. So maybe for my y values, I'm not terribly interested in having negative numbers of birds, but I want to go up to like 10,000. And I'll set my y scale to about 100. So each tick mark is 100. And see if this helps me out. Yeah, that's somewhat helpful, right? This gives me a much better picture than I had before. And if we wanted to know, so the thing I'm not looking for here is, what we want to try to do is we need to solve the equation x cubed minus 63x squared plus 942x plus 2620 equals 3,500. That's what we're trying to do. We're trying to solve this equation. And we can solve it graphically a bunch of different ways. One of the ways is like Mark was saying here. So I enter my function, I hit y equals, I enter my function, and then I can come over to a table here. And I can scroll around and see when the y values get to 3,500. So what do we have? I see right here. So on June 1st, right, x equals 1. This is exactly equal to 3,500. And I should look and see if there's anywhere else. So let me keep scrolling because we know it increases for a while and then decreases. Yeah, look, here's another one. So on the table, we see that x equals 1 and x equals 22 are solutions. And if we go back to the graph, based on the shape of the graph, do you expect to find any more solutions? I don't, right? So over here, when x is equal to 1, we're not going to see it exactly, but when x is equal to 1, we hit this y value, and then we go up, and then we come back down, and we hit that y value one more time. Like right around here. Yeah, somewhere right around here. And those are the only two times this function attains that value. Those are the only two times when this function and the line y equals 3,500 touch. And that's really what I'm looking for. I'm looking, solutions to this equation are places where this graph touches this graph. And I think Mark nailed it. By far the best and fastest way to do this is to look at the table, right? Just scroll through your table. So again, what did I do in the calculator here? To get the graphical representation, I typed in the function f of x, right? My bird population function. I adjusted my window to some settings that made sense for this problem. June has 30 days. This thing just models the population of birds in the month of June. So I set my x min to 0 and my x max to 30. Because that's how many days there are in June, just 30 days, right? I'm not really interested in negative days, you know, and I'm not interested in days more than 31. And then I set my y min to 0. I'm not interested in having a negative number of birds. I'm just interested in the population of birds, which is certainly always greater than or equal to 0. And I set the max to 10,000. Where did I get 10,000? Well, I've got 2620 here. I've got 3,500 here. And I've got a function that could move around quite a bit. I'm just guessing, but since these are both like, you know, bigger than 2,000 in the 2 to 5,000 range, I picked 10,000 just to be a kind of reasonable safe upper bound. And I changed the y scale to 100 just so it wouldn't look so cluttered. You could have left this at 1 and you'd still get a fine picture. Right. The other thing I'm graphing here is the line y equals 3,500, because I know that I'm trying to figure out where this function is equal to 3,500. And graphically, that's where those two things touch. Now, the way we actually found these numbers, x equals 1 and x equals 22, we could have estimated them by using the trace function here. And that, you know, we can walk around along this graph and see when we get close to that line. It looks like it's about 22. But if we wanted to know with greater certainty, the move is to use the table. Hit second in graph, that will bring up your table. And we just scrolled around here until we found this function being equal to 3,500. And there were two places we found it doing that. And up here, when x was 1, this was 3,500. And scroll and scroll and scrolling, looking at those y1 values. When we get down to x equals 22, here we hit 3,500 again. Yeah, so definitely the TI 83, 84, these are a big thing in college algebra. You really do need to get to know these. And I'm sorry that I don't have more built into this course for that. This course was designed back when these calculators were used a lot in high school and places. And I think now people are coming into this class with a lot less experience using the calculators. The learning commons. Say it like this. I think has a rental math support center. That's a good question. I know that we used to have, what do you call them? Like little meetings, little kind of tutorials for the calculator, workshops. But since COVID started, I don't know if we still do those, but there should be. Here we go, graphing calculator help. These are the things we have. So here, scroll down to the bottom of this. For it is a powerful tool, and you want to learn how to use it if you're not super comfy with it. If there's anything in particular that you guys want to see, I'd be happy to show you. But yeah, that is how we handle this. Trying to solve this equation by hand would be very hard. Not impossible, mind you, not impossible. But the tools that you would need to solve this equation by hand aren't things that you're likely going to see until I get you in pre-calculus. It's called the rational roots theorem. It shows how to really subtract this over and then factor this apparatus. But because this is it's not a trinomial, right? This has 4 pieces. It's a cubic polynomial. Factoring those are a little bit harder. Okay, what else would we like to see, guys? (13), part 2, number 9. Okay, I think that is our practice with roots and rational exponents, right? 13, part 2. Number. Be good over there, Hammy. All right. So depending on the last math class you took, this may be entirely review, or it may be something you haven't seen or haven't seen in a while. So they want us to use positive exponents to rewrite this expression. Let me see. It might be worthwhile. No, nah, we'll just dive in. So the good news is there aren't any negative exponents here to worry about. We just need to figure out how to write this thing. So we have this the square root of c times the 4th root of c. And I like to put a little tail on all of my radical symbols, all of my root symbols, to tell me where this thing ends. I'll zoom in here so you can see the 4. So my first step here would be to rewrite this as c times c to the 1/4 all to the 1/2. Right, so this outer root here, this is a 1/2 power, and the inner root here, this is a 1/4 power. So kind of the thing that's going on here is that the square root of some stuff is the same as that stuff to the 1/2 power. And if you see like an nth root of some stuff, that's the same as that stuff to the 1/nth power. So when you see the radical without anything here, it's assumed that that's a 2. And if you see the radical with something else here inside the little check mark, then that's the nth power. So this is all I've used so far. The other properties I'm going to need here, if you have 2 things all being raised to some power, You can take each thing and raise it to that power as long as the two things were being multiplied. And here, thankfully, these are being multiplied, so I'll be able to use that rule. And then sort of the other rule that we're going to need here is that if you have something like this, like a number or a variable or whatever raised to some power, and then that whole thing raised to another power, you multiply those powers. And there will be one last rule, but when we get to that, I'll see if you guys can help me out. So if I use this rule now, I can give this 1/2 power to each of these two pieces. That's the same as c to the 1/2 times c to the 1/4 all to the 1/2. All right, so I'm just taking this 1/2 power and giving it to this and this separately, following this rule. This is now c to the 1/2 times, according to this bottom rule here, this will be c to the 1/4 times 1/2. And if you multiply 1/4 and 1/2, you get 1/8. Are there any questions up to here? I think my cat might be getting enough fight outside. So the last rule I need to clean this up, if I have a to some number times a to some other number, if you're multiplying like bases, you can add the exponents. So if I wanted to write this as a single power of c, this would be c raised to the power of 1/2 plus 1/8. And then we need to go ahead and do the arithmetic here. How do I add 1/2 to 1/8? Well, I need to have a common denominator. That denominator is going to be 8. So if I multiply the 1/2 by 4/4, then that will become 4/8 plus 1/8, which is 5/8. So this is c raised to the power of 5/8. There are other ways to go through this. I think this is maybe the most natural way. You could also combine these first and then give them the 1/2 power. That would work. Are there any questions about any of these steps? These rules for exponents, they're useful when we talk about power functions, for sure. They're also going to be really useful when we talk about exponential functions. So it's important that you're comfortable with all the orange things. Any questions about any of the steps we did here in black, or any of the rules here in orange? Okay, if not, the next homework problem that was requested is homework 11, number 18. Over here. And the little activity I have planned for us today does involve proportionality. Come on. I don't think that's doing what it should be doing. So let's try this one more time. 11. There we go. All right, we wanted to see number 18 here. 18. All right. Use this function to answer the following questions. Yes, this is a good problem. I'll tell you right now, okay? A problem like this will show up on your test. A question of this nature will absolutely show up on your test. This is homework 11, problem 18. If g of x is a function 9x to the negative 3, part A, if x doubles, then g of x gets multiplied by what? If x is tripled, g of x and g of x gets multiplied by what? So I'm really glad that Justine asked about this. This is a great problem. And back when we talked about proportionality arguments, these were some of the things that we looked at the closest, but they're also some of the hardest to really wrap your head all the way around. So I'm really grateful that we're looking back at one of these. What does it mean to say that x doubles? Symbolically, in terms of algebra, what does it mean to say something doubles?
Would it be 2 times that variable?
Yeah, exactly. This means x gets replaced by 2 times x. So what we should look at here is g of 2x and see what we get. If I replace x by 2x in this expression everywhere, then I get g of 2x equals 9 times 2x to the negative third power. Now let's look back over here. Do we see a rule that could be useful here? Yeah. So if you look at that third rule, a times b to the m is the same as a to the m times b to the m, and apply that to the 2x to the negative 3, you get 9 times 2 to the negative 3 times x to the negative 3. Everybody see that? It's this rule. And now 2 to the negative 3 is 1/8. And I'll walk you through why that's the case. This is 9 times 1 over 2 to the positive 3 times x to the negative 3. All right, that's how negative powers work. Kind of the rules that we're using here, I'll write them down. A times b to the m, that's a to the m times b to the m. Another one here is that a to the negative m is the same as 1 over a to the positive m. This second rule wasn't on the last page because the last one we didn't have any negative exponents to deal with. So this is 9 times 2 cubed is 2 times 2 times 2. That's 8. So this is 1/8 times x to the negative 3. And then the only thing I would do here is shuffle that 1/8 out front, right? The original thing had a 9, had an x to the negative 3. Well, here's my 9, here's my x to the negative 3. So if I want to, I can, everything here is being multiplied, so I can do that multiplication in whatever order I want. And I think rewriting it like this makes it easier to see what's going on. This is 1/8. And this piece right here is my original function, g of x. So if x doubles, then g of x gets multiplied by 1/8. Hamlet, be good, bub. Sorry. That's what's going on here. When x doubles, that means we're going to replace x by 2x. And we clean everything up. What we end up with is 1/8 times g of x. So when x doubles, a 1/8 pops out, and then the old function shows back up. Questions about what we did here? So if g of x was like measuring how intense the sound was from a speaker x feet away, if you walk away, if you double your distance, then the intensity goes down by a factor of 1/8. Right? That's another way to say this sort of thing. If x goes up by a factor of 2, then g of x is reduced by a factor of 1/8. There are things, lots of things, in fact, in the real world that operate this way. Let's see if we can handle part B here. So having seen how we do part A, who can tell me how to set up part B? We're asking if x is tripled, then what happens to g of x? Good, yeah, we should replace x by 3x. So kind of my first line is going to look like g of 3x. And g of 3x is 9 times 3x to the negative 3. Is everybody comfy with this? What I'm doing is in here, right? In here where there's an x, I'm replacing, and we always do this in parentheses. I think that's maybe one of the most important things. Anytime you're working in function notation, anytime you're going to replace the variable in your function by something else, you need to do so in parentheses. We're going to replace x here by 3x, which means this piece becomes 9 times 3x to the negative 3. Alrighty. What now? Yeah, Mark. Is it a question about this problem? Oh, okay, yeah, here, let's go ahead and finish this up. So in order to finish this, we got to proceed. We got to do the same thing we did with this last guy. I need to figure out what this is going to turn into. So the way I do that, I say, okay, this is 9 times 3 to the negative 3 times x to the negative 3. And I know the 9 and the x to the negative 3, those are a part of the original function g of x. So I want to figure out what to do with this 3 to the negative 3. To do that, I'll figure out what that is. That's 1 over 3 cubed, which is 1 over 27. 3 times 3 times 3 is 27. And then I can shuffle that 1/27th out front. And what's left here is 9x to the negative 3. And this 9x to the negative 3 I recognize as being the old function g of x. So this is 1 over 27 times g of x. So here I would say when x triples, g of x gets multiplied by 1 over 27. I'll say it one more time. This will be on the test. Right? There will be a problem on the test where you either are given or have to come up with a power function. And then I ask you, if I double the input, what happens to the output? Or if I triple the input, what happens to the output? Something like that. All right. Mark, you said you had a question.
Yes. When you are talking about odd and even functions, the only way that you know if it's a odd or even function is if you do the test with like the f of x equals f of x, f of negative x, correct?
Yeah, so if we want to know whether a function is even or odd, remember, so even and odd functions. An even function, this is one that satisfies f of negative x is equal to f of x, and they'll have y-axis symmetry. So if you're wondering, is my function even? One option is to graph it. If it has y-axis symmetry, then it is. But another way, if you want to check if f of x is even, we replace, just like we were in this last guy, x by negative x and try to simplify f of negative x into f of x, because f of negative x should be equal to f of x if f is even. And similarly, if f is odd, that means f of negative x is negative f of x. These have origin symmetry. And to check here, we replace x by negative x and try to simplify f of negative x into negative f of x. Is that kind of what you were asking, Mark?
Yes. Okay. And then my other question too is, sometimes there's a confusion with me, is an even and odd function. has nothing to do whether it's an even degree or an odd degree polynomial. Is that correct?
That is correct. Yeah. So for a polynomial, if all of the powers of x are even, then that will be an even function. And if all the powers of x are odd, then that will be an odd function. But just the degree being even or odd doesn't tell us that the function is even or odd.
Okay, and thinking one more thing.
Sure.
All even degree polynomials, their tails point in the same direction. Is
Yes.
that true or false?
That's true. That is a true statement. So the degree determines the end behavior, for sure. So if you have an even degree polynomial, the end behavior will either be up on both sides or down on both sides. And if you have an odd degree polynomial, the end behavior will be up on one side and down on the other side. Cool. All right, what else would we like to see? We've got a little bit of time before I want to start on the actual little activity here. We can look at some more problems from the power function stuff. We can look at some more problems from the polynomial stuff. What would you guys like to see? What other homework problems would you like to look at?
Can you keep the even odd functions thing up for just 1 second?
Yeah, do we want to do an example with these?
Yeah.
All right, while you're writing that, I will refill my coffee and then we'll do a quick example. Oh. So I added a little example down here. We want to determine whether the function f of x equals x over x squared plus 1 is even, odd, or neither. I think it's wise to look at the graph first, because we can use our graphing calculators to get an idea of what the graph looks like, and that will at least give us a guess. So I turn on my calculator, I come over here to y equals, I clear out whatever is there. Clear this out. And then up here in y1, I'm going to type x divided by parentheses. And remember, you got to, if your top or bottom of a fraction has more than one term, you need to put it in parentheses. X divided by parentheses x squared plus 1, close parentheses. And make sure it looks like this, right? If we're really being careful, we would put the top in parentheses also. But since the top is just x, it's just one term, we don't need to. But if there was more than one term up here, even like 2x or x plus 5, anything like that, then the whole top would have to go in parentheses. Make sure my window settings are something reasonable. So I'm going to change these back to the standard viewing window, which is the -10 to 10 window. And then hit graph. And what you see is I can't really tell much, but what's wrong with this? It's that I'm too zoomed out along the y-axis, right? So if I want to zoom in along the y-axis, maybe I just change this to like -3 to 3. Oh, that's better. In fact, it looks like this thing never gets bigger or smaller than 1. I can change these to like, let's do -1.5. So 1.5. That way it's not crowded. And now we get a really nice picture of this graph. Okay, so based on the picture here, do we think this is an even function or an odd function? What sort of symmetry? Does this have y-axis symmetry? It's true, this is not a polynomial. Yeah, this is a good point. The function that I'm giving you here is called a rational function, right? This isn't something from homework 12. This is like something from homework 13. This is a rational function. So any of the rules for like tricks for polynomials wouldn't work here. Saying, oh, all the powers of x are odd or all the powers of x are even. That won't work here because this is not a polynomial. But looking at the graph exhibits origin symmetry, right? This graph appears to be symmetric about the origin. So we would think that this is odd. I'd say from the graph. And we can provide a quick sketch. Graph, which looks like this. We think f of x is odd. Algebraically, if I had to show you algebraically that this satisfies the definition of an odd function, that means I would have to look at f of negative x and try to simplify that into negative f of x, right? Like it says above. To check if f of x is odd, we replace x by negative x and try to simplify f of negative x into negative f of x. This. So let's see if we can do that. F of negative x is what I get by taking all the x's that show up in here and replacing them in parentheses with negative x's. That looks like this. Kendra, the test is just going to be on the material that we've covered since exam 1. So it's not comprehensive. It doesn't cover everything from the start of the semester. So things like linear functions, linear regression, average rates, well, I don't want to say that, but linear functions, linear regression, slope, those are not going to be tested for very heavily on here. I certainly could ask you questions that involve them, but the test is designed to get at just the material since exam 1. All right, who can help me simplify this? What is this down here? Negative x all squared. Well, it's negative x times negative x, right? When you square something, you're multiplying it by itself. What is negative x times negative x? The negatives will go away, right? Multiply a negative by a negative and you get a positive, but it's not positive x. It's positive x squared, right? Negative times negative, and the same in negative 2 times negative 2 isn't positive 2, it's positive 4, right? You have to multiply the x's also. So downstairs here, I have x squared plus 1. And then upstairs here, this negative x in parentheses, there isn't any number multiplying this. There isn't any power here that I have to be careful with. That's just negative x. So we have negative x over x squared plus 1. And that really is the same as negative x over x squared plus 1. Just like how negative 5 over 2 is the same as negative 5 halves, right? Having a negative upstairs here like this is the same as having a negative out front like this. And the piece that's left over here, look at what this is. This is my original function. So this is negative f of x. And that was my goal, right? I wanted to see if I could simplify f of negative x into negative f of x. That's the definition of an odd function. So look at what we have here. It's exactly the definition of f of x being an odd function. So we win. All right. Even and odd functions. Good stuff.
What would it look like if it was neither odd or even?
We can take a look at, let's do another example. And give us a couple more. Let's say, all right. So this first guy, x squared over x squared plus 1, we can fiddle with him. And the second guy, x cubed minus 2x squared plus 4, we can fiddle with him. This one is a polynomial, g of x here. So the shortcut that I mentioned earlier should have you thinking whether you should have an idea. I'm not going to ruin it right now by restating that shortcut, but if you remember it, you should have the answer for this already, but I'll remind you afterwards. Let's start with this guy. F of negative x here would be negative x squared divided by negative x squared plus 1. Just everywhere there is an x, I write parentheses negative x instead. And in the same way we simplified negative x squared to x squared in the previous problem, this is just going to be x squared, and this is just going to be x squared. And that negative x squared is negative x times negative x is positive x times x is x squared. So this piece over here is x squared, this piece down here is x squared, and 1 is still 1. And this is my original function. This is f of x. So fx is even, because f of negative x simplifies to f of x. And we could have seen that in the graph also. Quickly here, let's see. If I change this x to an x squared, and divide, nope, x squared, and then divide by parentheses x squared plus 1. Oh, shit, all right, fuck me. X squared divided by parentheses x squared plus 1. Like this. my scales, I might need to play around with things a little bit more. Oh, no, this is fine. You see, we have y-axis symmetry here, right? It's symmetric about the y-axis. We could have guessed that this would be even. The other function, g of x, we can take a look at him. He's x cubed minus 2x squared. Oh, shit. It's a thing with the 84 that I'm not used to. We gotta push over to get down out of the power. Minus 2x squared plus 4. Here, my scales aren't going to be appropriate for this. Yeah. Let's go. Just for fun. Oh, no, sorry. Negative 10 to 10 is fine for these. The y values are not nearly big enough. Let's change this negative 50 to 50 or something. You get, yeah, something like this, right? And this doesn't exhibit any sort of symmetry. So I don't think that this is going to be even or odd. But what does that look like algebra-wise? G of negative x here is negative x cubed minus 2 times negative x squared plus 4. Negative x squared, we already know that that's the same as x squared. What about negative x cubed? Well, that's the same as negative x times negative x times negative x. That's 3 negatives multiplying together, so it's going to be negative at the end. And the thing that we get out is x times x times x. That's x cubed. So parentheses negative x cubed is the same as the negative of x cubed, right? The kind of take-home message for this, by the way, is that if you raise negative x to an even power, it gets gobbled up. And if you raise negative x to an odd power, the negative gets spit out. That's kind of the pattern here. So this is going to be negative x cubed minus 2 times. We know what this is. This is just x squared plus 4. But this is not the same as negative g of x. So what we can do is we can separately write down what negative g of x is. That would be the negative of x cubed minus 2x squared plus 4. And that would be negative x cubed plus 2x squared minus 4. So this is not g of x. So it's neither g of x nor is it negative g of x. So g of negative x doesn't simplify to the original or to the negative of the original. This is what the negative of the original would look like. And the original itself is up here. So this guy is neither even nor odd. Right, here we have this written just to check and see what negative g of x would look like, because this kind of looks like it might be that, but it's not. Okay. How are we on time? 10:32. Okay, so what I want to do now is pull up. I have 1 or 2 extra problems here that I'd like you guys to take a look at. And instead of going into breakout rooms, having everybody work on this separately, I just want to work through these together with you guys. And you interact with me a little bit here, give me some responses, and I'll give everybody credit for the activity today. It says, on planet Euler, the time, t, it takes for an object to fall is directly proportional to the square root of the distance h it has to fall. Suppose it takes 3 seconds for the object to fall 16 feet tall. Fall, that's a typo here. No, shut up. So what equation relates t to h? Can we find the constant of proportionality and then answer how long would it take to fall from 100 feet? And give your answer as a decimal rounded to the nearest 10. I don't know why that keeps doing that. Okay. So this is a problem I took a few semesters ago straight off of my old exams. One of my old exams had this problem verbatim. What do we want to do?
Wouldn't it be t equals the square root of h, and then there'd be 3 equals the square root of h, based on the information it gives us?
So that's very close. They say that the time t to fall, distance, time t to fall is directly proportional to the distance h it has to fall. So t and the square root of h is directly proportional to the, oh, sorry, to the, that's not what it says, to the square root of
Do you want us to just write these down on
No.
paper?
No, you don't have to write anything down. Just take notes along with me. Just treat this like another example.
Okay.
So the problem here says the time t is directly proportional to the square root of the distance h. So there is an equation we can write down from this, but it's not just t equals the square root of h. This word directly proportional, this is the key thing, right? This means it's equal to a constant times the square root of h. So the square root of the distance h is root h. They said t is directly proportional to the square root of the distance h. So this is what we would get from that first piece. This is the square root of the distance h. And this is the time t it takes to fall. So if I say those two things are directly proportional, that means the first one is equal to a constant times the second. That's all that means. They also said it takes 3 seconds for the object to fall 16 feet. So we want to know, can we use that information to solve for the constant of proportionality? Well, if the time is 3 seconds when the height is 16, that means 3 is equal to k times the square root of 16. In other words, 3 is equal to k times 4, which means dividing both sides by 4, that 3/4 is equal to k. So that's the constant of proportionality. So if I wanted to know how long it takes to fall from 100 feet, which is what we have in part B, this is approximately true, by the way, guys. The numbers aren't perfect, but they're very, very close. The time it takes to fall on Earth is directly proportional to the square root of the height. And these constants are not too far from the truth. So if I wanted to know how long it takes to fall from 100 feet, what would I do? Thank you to Jacob and Kendra in chat. I appreciate that. Yeah, we need to plug this shit back in here. Well, we now know. And I call this updating the equation, right? We now know we can update our equation here to t equals 3/4 times the square root of h. And this is true for any height. If you want to know how long it takes to fall from 10 feet, 20 feet, 30 feet, 100 feet, 1,000,000 feet, in theory, this is how you would find out. You just plug that in for h. So to fall 100 feet, it will take t equals 3/4 times the square root of 100, which is 3/4 times 10. The square root of 100 is 10. And 10 and 4 have a shared factor of 2. So you can think of this as 30/4, or 3/4 times 2 times 5, however you want to do it. When you clean up the shared factor of 2 there, this will become 3 times 5/2, or 15 halves. But the problem asked us for a decimal rounded to the nearest tenth. 15/2, if you put that in your calculator, that's 7.5. So it takes 7.5 seconds to fall 100 feet. Yeah, excellent. Thank you, guys. Okay, I have another question like this, having to do with inverse proportionality, and this is the last thing I'm going to subject you guys to today. I do also have, let me see, before I forget, there is a project that I'd like you guys to work in addition to this review. So in the syllabus, there's a project associated with each test. Before we get too short on time, let's see, do I have it in here? No, I don't. So I'm going to be adding a project here. I want you guys, you take your time to work it. Let me just show you what it is. As long as you get it to me by the end of the day on the day of the test, I'll get you full credit for it. It will help you prepare for the test. Why are you always calling me? Tool, 14, screen 20, yeah, here. So I'll be uploading this. You can think of it as extra review for the test, but you do need to get it done. Oh wait, let's see, project. Yeah, this is fine. Good. All right. I'll make a few little changes to this to help it fit what we've covered for exam 2 a little bit better and be uploading it. Just make sure you look in the Canvas assignments for project 2. it'll be due by 11:59 on the day of the test. All right, the last little bit of activity question here. This. A student's scores varies inversely with the number of alcoholic drinks they consumed the week before. So the score on the final varies inversely with the number of alcohol drinks the week before. Last semester, we had 15 drinks the week before and scored 60% on the final. What score can be expected from consuming 25 drinks? So we're not sugarcoating these numbers. I've been to Midtown. I know what y'all do. 15 drinks is modest for a week, an undergraduate here in Gainesville. The trick is to, just like the last problem, start by writing down an equation. The idea here is that we're just walking you through it a little bit less gently. So rather than telling you step by step, find the equation, find the constant, then plug in, it's up to you to take all of this language and know to do those things. But it's the same sort of problem. The only difference here is that now we have varies inversely rather than directly proportional. And also, we haven't chosen any variables for you. You have to pick the variables you're going to use. So how do I get started here? What would be the first thing to write down?
K would now be 1 over K, right?
That's not quite what varies inversely means. So the constant of proportionality is still just going to show up upstairs. The varies inversely kind of tells us what the variables do, not what the constant does. So I think a good first thing to do is to pick some variables. Let's let the score on final, what do we want to call that? And the number of drinks. You know, we can use like X and Y, or whatever variables you guys want, but we need to start by picking some variables. Maybe I'll call this Y, and I'll call this X. So what we're saying is that the score on the final, Y, varies inversely with X. That's what we have. So we need to figure out how to write this down as an algebra equation. This means that Y is equal to some constant, the constant's still upstairs, but times 1 over X. That's the idea. So this and this mean the same thing. And I know that these are a little bit tricky. That's why I wanted to do one extra bit. Yeah, if you want to write it as K over X, your homework wrote it like that sometimes too. This is fine. Just remember which one's the constant and which one's the variable. Here, let me say, I'll say it like this, or Y equals K over X. These mean the same thing. All right, so here's the equation. I need to find the constant K. So I keep reading the problem. Last semester, 15 drinks and 60% on the final. So when X was 15, Y was 60%, or just 60, let's say. So we know that 60 is equal to K over 15. And now I can use this to solve for K. If I multiply both sides by 15, 15 times 60 is actually going to be quite large here. Trust my arithmetic this early in the morning. 900. So I get 900 is equal to K. So now we know that Y is equal to 900 over X. This is my updated equation. And if I want to know what kind of score can this dude expect if he drinks 25 drinks the week before his final, he can expect Y equals 900 over 25 for his score, which is 900 over 25. $36. We can expect a 36% on the final. So inversely proportional means the first thing, the first variable, is equal to some constant times the reciprocal of the second variable. Or equivalently, the first variable is equal to a constant over the second variable. So the score on the final varies inversely with the number of drinks, means the score on the final is equal to some constant over the number of drinks. The first thing you need to do on these sort of problems is pick some variables, though. I think these problems can be intimidating at the start because they don't tell you what sort of variables to use. Yeah, thank you, Jacob. If you wanted to work this, by the way, with the percentages as decimals, you could do that. And I think in that case, Jacob, your answer K equals 9 would be correct. All right, so I worked with these percentages just as numbers, and that's fine also, as long as you're clear with your notation. Alrighty, last thing before I go again, look, I'll post an announcement just like I did before exam 1, so you can get the project there, where you can get project 2. I'm going to make a few little changes to this. Think of this as extra study material. You also have the review up in my math lab. The only things I'm asking you to do between now and the test is complete this review and also complete project 2. I'll be posting project 2 a little bit later today. I want to make a few small edits because this is a little different than it was last semester. And that is it, guys. So please go ahead and get started on the review. If there's any of these old homeworks you haven't finished up, please send me a Canvas message letting me know which ones you need open. I will open them. You should do the homework first, then the review for the test, then the project. The project is going to be hosted up in Canvas. All right. I hope you guys have a lovely rest of your day. If you haven't done the test 1 reflection, please get in there and do that shit. The sooner you do that shit, the sooner the department will get off my ass about it. It is for your own good. They're setting up something called a DLP, Digital Learning Plan, and down the road here at Santa Fe, it may affect things if you don't do that. I don't know exactly what the intent or bureaucracy is behind it, but trust me when I say it's something that administrators are looking at, and we really want you guys to do. So please, if you haven't done the test 1 reflection, do that. Make sure you do that before test 2. Finish all the old homeworks, then do the review in MML, and then do the project, and you will be in good shape for test 2. I do have a normal office hour today at 11. So if you want to come over there and chat about anything, I'll be there. Otherwise, just make sure you show up on your phone in Zoom on time for the test on Thursday. That's it, guys.
Thank you.
Of course, take care.